Okay, so today I will start with this half adder and full adder. So earlier we saw what is digital signal and what are the basic gates we are using to make a digital signal. Those are AND gate, OR gate, NOR gate, NAND gate, etc. So we will see that how we are doing different applications for this digital signal. So we have half adder and full adder to do various addition and subtract addition in the binary. Okay, if we have two numbers and if we have to add it, so how we will do with this half adder. So these are the Boolean expressions. So this is not in the syllabus, but it is important for you to understand this half adder. So we can standardize the Boolean expression by using two standard forms. Okay. So one is our sum of products, which is also called as SOP, and other is product of sum. Okay. So by like in your mathematics, you might have done this BODMAS. Okay, there is a rule we have to multiply the inside terms in the sequence. Same way we have the sum of products in a Boolean expression. Okay. So as we are having this name sum of products, so what is sum of products? It means first we have to do this product term. Okay, then we have to do sum of these products. Okay, for example, in a mathematical form, if we have this number 1 into 2, so these are the products. This is the first product. 1 into 2 into 3, this is the second product. And this 4 into 5 into 6, this is our third product. Okay, so what we have to do, these are our three products and then we have to sum it. So that's why we are calling this as sum of products. Okay, so for example, if we have equation like this, so this dot, it means it is a AND gate or we are doing the multiplication. So here also we are having another AND gate, and here also we have another AND gate. So these are the three AND gates. So these are the product terms. Okay, so as it is sum of products, so then we will sum all the products and it will become a sum of products. So this is an example of sum of products, and we will only be using the sum of products for our evaluation. One more is there, it is product of sums, but we won't be using this because this is little bit complicated. So you can either make the circuit with the sum of product, or you can make a circuit from this product of sum. But I would suggest you only do sum of products, because this product of sum, it is just the opposite of the sum of product. Okay. So what is product of sum? So first, as it is product of sums, so first we have to do the summing part. So here, if we give an example in a mathematical form, so we will first have the sum. So like there is a summation of 1 plus 2. This is our first term. Then second term is 1 plus 2 plus 3. So this is our second term. Excuse me. And 4 plus 5 plus 6. Excuse me, 1 minute. If this is our third term, then these are the sums. Okay, and then we will product, as it is product of sum. So we will multiply all the sums. So we will multiply this first term, this second term, and this third term. Okay, so this will become a product of sum. So in Boolean expression, we will get it as a plus b. So this is the summation part, a plus c. And this is the second summation part, and this a dash plus b dash, this is the third summation part. Okay, so we will product this. So we will multiply this a plus b into a plus c into a dash plus b dash. Okay, so this is how we are doing the product of sum. So any doubt in the sum of products and product of sum? Hello?
No,
Any
ma'am.
doubt? Okay, thank you. So in Boolean expressions, we have done this. So if we have only one bit, okay, Here we are not saying bit. Here for this logic gates we will say inputs. Okay, here we won't say bits because bit is only one. Here we are only using one bit, so here we are using number of inputs. So if we have only one input, so we had combinations of 0 and 1. So how can we write 0? We can write 0 as a bar or a dash. Okay, here I can't write a bar, so I have written a dash. So it is the same as a bar. And 1, how can we write? If the input is a, so 1 we will write it as a. Okay, and for two inputs, if we have two inputs, then the combination will be 0, 0, 0, 1, 1, 0, and 1, 1. So how can we write this combination? So actually, this is, we are using the sum of products. Okay, we will first do the products and then we will do the sum. So we have applied sum of products here. So we have to multiply these inputs. Okay, so for a 0 0, it will be a dash into b dash. For 0 1, it will be a dash into b. For 1 0, it will be a into b dash, and for a 1 1, it will be a into b. Okay, this is clear to you how we are writing the expressions? Is it clear?
Yes, ma'am.
Okay, so how we will write this expression? 0 0 0, how we will write this?
A bar, B bar, C bar.
Okay, 0 0 1.
A bar, B bar, C.
This one, third one.
A bar, B and C bar.
Okay, and this last one.
A, B, C.
Okay, thank you for this. Okay, so this is how we will write the expression, seeing the inputs. This is sum of products and this is product of sum, whatever you said. So in sum of products, we will have a min term. We will call it as min term, and it will be expressed with the small m. Okay, so this first term will be m0. The second term will be m1, third will be m2, and this last will be m7 because total 8 combinations are there for 3-bit input. And for product of sum, we will not be using this, okay, because this is little bit complicated. What happens in a product of sum, actually it becomes opposite. So here, as we are taking a dash, b dash, c dash, here what we will take, we will just take the opposite of it. So it will become as a plus b plus c. So where there is 0, we are using a, and where there is a 1, we are using as like c dash. Okay, so that's why we are trying to avoid this product of sum. You can make the circuits with sum of products also. You can make the circuits with product of sum also. But this is a little bit complicated, so we will be avoiding this. Okay, here you can say for 1 1 1, it becomes a dash plus b dash plus c dash. Okay, so we are avoiding this product of sum. We will only use sum of products. So wherever we have an input, okay, so there we will multiply all the inputs or dot product all the inputs. So if we have 0 0 0, we will say it as a dash into b dash into c dash, or a dash into a dash dot b dash dot c dash. Okay, so this is how we will do sum of products. So, what is the rule for sum of products? So, wherever in the output, if we are getting, I will read this, we will only observe for the cases where we are getting 1 as a output, called as min terms. Okay, so here we will only here only inputs are there. So, if output is there, and in the output, wherever we are getting a 1, only those cases we will consider and only those inputs we will take. Okay, so we will first AND gate all the inputs. So wherever there is 1, we will AND gate this, and we will take min terms, whatever the min terms are, first min term, second min term, third min term. And what we will do, we will first AND gate the inputs, and then we will combine all the cases with OR gate. Okay, so uh, this is our first case. So we will add first M0 plus M1 plus M2 plus M3 plus M4 wherever we are getting a 1. Okay. And POS just opposite happens. Here we are considering the cases where wherever we have a 0. Okay. And that is called max term. So wherever we get a 0, only those cases we consider. So we OR gate the inputs and we AND gate the all the cases. This max term. So here is an example of sum of products. So here we can see these are the inputs A, B, C. So we have to take the AND gate of all the inputs. So what is the rule for sum of products? Wherever we are getting a 1, we will consider those cases only. Consider those cases. Wherever we are getting a 0, it means it is off, it is not working. Okay. So that's why we will only use only one cases. For this only we need the output. If we also consider this 0th, we will also take this gate for combination for this 0th term. It means that it will become it will switch on in this also, so that will be wrong. So we have to take only those cases, means we have to switch on the system in this second case, for this fourth case, and for the sixth case. Okay. So for the second case, what will be the combination? For the second case, what will be the combination?
A bar, B bar, C.
Hmm. So it will be A bar into B bar into C. Okay. So here we are writing this first case. This second case, what will be the combination?
A bar
A
B.
bar, B, C.
Hmm. A bar, B, and C. Okay, this will be the second case, and this third case.
A, B bar,
Hmm.
C,
And C. Okay.
C.
So this is what we are using in the sum of products. In this product of sum, it will just become the opposite. Okay. So we won't see this product of sum. Anyone has any doubt in the sum of product?
Ma'am,
Hmm.
how it get 0 and 1 F in F?
No, this is some combination. Like we are just giving the example. No relation
Okay,
is
ma'am.
there.
Oh,
Okay. This is just
okay.
an example. So for sum of products, what we will do, we will first see the outputs. Wherever we are getting a 1, we will only consider those cases. Okay. So for wherever we are getting a 1, we will see all the inputs. We will AND get all the inputs, and whatever the cases are coming, we will product the sum. We will do the product, sorry, we will sum of the products. So first we will take the products and then we will add all those things. So this is becoming our sum of products. Okay. You can also make the circuit with this product of sum, but as it is opposite, it is very confusing. So I'm leaving this part. Okay. So we will use the sum of products to make the adder. So what is an adder? We are adding 2-bit numbers. Uh, so these bits are single bit. Those are not, we can't add 2 bits. If we have to add 2 bits, what we will do, we will take two adders and we will add it. Okay. So a single adder will have only 1 bit input, and there are two kinds of adder. One is half adder and one is full adder. Okay. For half adder, we will take two individual bits together, and for full adder, we will take three inputs. And for both half adder and full adder, we will get a sum and a carry. Okay, so we will first say what is half adder. So in half adder, this is the symbol for half adder, where we have A and B. So A and B are input, and we have two outputs, which is sum and carry. Okay, and you have to add write half adder inside this box. So half adder take adds two binary variables and yields a carry, and does not accept a carry from another circuit. This is from your book. But to understand this, you can write a half adder performs 2-bit addition. Okay. So what is 2-bit addition? Earlier we were doing this logical addition. So 1 plus 1 was also 1. But here we are doing binary addition. So don't get confused in this. Okay. We are doing binary addition over here. So what is binary addition? If we add 0 plus 0, then we will get a 0. If we add 0 plus 1, then we will get a 1. If we add 1 plus 0, then we will also get a 1. But if we add 1 plus 1, we are getting 1 0. Can you tell me why we are getting 1 0? Anyone? Why we are getting a 1 0? Think about the binary expressions. Binary we did now. Convert. This is a binary term. Okay, we have to convert this binary to decimal. So what we will do to convert this binary into decimal? Okay, what is this 1 plus 1? This value is 1, this value is 1. So 1 plus 1 in decimal, what is the value? This 3 plus 4 is 7. So 1 plus 1, what will be the value in decimal?
2, ma'am.
2. So if we, this is a binary term. Okay, 1 plus 1 will be 2. So this is a binary form. So what we will do, how we will convert this binary to decimal? We will do not 2 to the power 0 and 2 to the power 1. So what is below 2 to the power 0? It is 0. And what is below 2 to the power 1? It is 1. So what will be the value for this 1 0? You forgot this binary part. Here we were doing now how we did this binary part. So 0 0, what we were doing, we were putting 2 to the power 0 and 2 to the power 1 over here. Okay. So how we were doing this? So what is 2 to the power 0? It is 1. And what is 2 to the power 2? It is 2. So how we were changing from binary to decimal, we were multiplying these terms now. So 1 into 0 is 0, 2 into 0 is 0. So that's why we are getting a 0. Okay. But what is the value? Our value is 0 1. So how we will multiply? We will multiply this 1 into 2 to the power 0. So 1 into 1 and 0 into 2 to the power 1. Then we will add these both terms now. So it will be 0 plus 1. So the value is coming as 1. So how we are representing a 2? We will multiply this 0 with 2 to the power 0. So it will be 0. And we will multiply this 2 to the power 1 with this 1. So that is, we are getting a 2. So 1 into 2 plus 0 is, we are getting a 2. You remember this part? Binary to decimal.
Yes, ma'am.
Okay, so what is the value for 2? We are, it is 1 0. Okay, for 2-bit numbers. So that's why we are getting, a 1 0 over here. If we add 1 plus 1, so we are getting a 2. Any doubt in this? How 1 plus 1 we are getting a 2? Hmm. Any doubt?
No, ma'am.
Okay. So what if we add 1 plus 1 plus 1? So in decimal, if we add 1 plus 1 plus 1, what is the value?
3.
So here what we do with 1 plus 1, we already got a 1 0. It is not 10, it is 1 0. Okay, don't say it is at 10. Okay, so what is this part we did, this first and second part. So what is this third part? We will add another 1 here. So if we add 1 plus 0, we are getting a 1. And if we add this 1 is there, so it will become 1 1. Okay. So 1 plus 1 plus 1, it is becoming 1 1. So what is the value for 1 plus 1 plus 1? It is 3. So this is in a binary form. So what we will do? We will do 2 to the power 0 and 2 to the power 1. Okay. So we will get 2 plus 1. So that is becoming a 3. Here if I show you this one, so 1 1, what it is? It is 3. So that's why if we add 1 plus 1 plus 1, so we are getting a 3. Any doubt in this? How 1 plus 1 we are getting 1 0 and 1 plus 1 plus 1 we are getting 1 1.
No, ma'am.
Okay, thank you. So in binary, we have to use only 0 and 1, and we have to do the addition and multiplication through this. So these are the rules. Okay. If we add 0 plus 0, we are getting a 0. If we add 0 plus 1, then we will get a 1. 1 plus 0 is also 1, because if 1 plus 0 in decimal, we are getting a 1. So if we put 2 to the power 0 here, so it will become 2 to the power 0, means 1 into 1, so we will get a 1. And because 1 plus 1 is 2, we are getting a 1 0, because here 2 to the power 0 and 2 to the power 1. So 1 into 2 to the power 1 is 2. So 1 into 2, we will get a 2. And because there are 3, so we will add 1 0 plus 1. So we are getting 1 1. So if we add put a 2 to the power 0 here and 2 to the power 1 here, so we will add 2 plus 1. So we will get a 3 over here. Okay. So here in binary addition, what we can see, if we add this 1 1, so we are getting two terms. So we are getting one carry. Okay. So what we will say that this is a sum part, this right hand side part. So this is a sum part and this is a carry part. Okay. So we have two inputs A and B. So So if we add 0, so we are doing binary addition. Okay, so we are adding these two numbers. So we are adding here, we are doing addition here, we are doing addition here, and we are doing addition here. So we are adding 2-bit numbers. Okay, so what if we add 0 plus 0? What will be the sum?
0,
And carry?
0,
Okay, if we add 0 plus 1, what will be the sum?
1,
And carry?
0,
Because 1 plus 1, we don't have any carry. Okay, that's why we are only getting a 1. If we add 1 plus 0, then what we are getting?
1,
And carry.
0,
So if we add 1 plus 1, so what is the sum?
0,
And carry.
1.
Okay, so this part you understood now.
Yes, ma'am.
So implementation of half adder and full adder. So we will observe the cases where we are getting a 1. So we will use the sum of products. Okay. So first we will AND gate the inputs, and then we will combine all the cases with OR gate. So this is, we are doing, first we are doing the sum, and then we are doing the sorry, first we are doing this product. So AND gate is the product, and then we are doing the sum part, which is OR gate. So we are doing sum of products. Okay. So half adder and full adder circuit, we have to make a circuit in such a way that it is a very small circuit, like minimum number of this circuits are required. Okay. So we have to make a circuit out of this, this is the theory part. Okay. So if we add 0 plus 0, then we should get the sum and carry. So this is the theory. So how we will implement it? We have to produce an energy. We can either use this wind energy or solar energy. If you are staying near the sea, what you will do, you will use this wind energy. And if you are staying somewhere in Rajasthan, what you will use the solar energy, because too much sun is there. Same way we have to, this is a theory. Okay, so this is a theory of our addition, how we are going to do the addition. So how we will make this come. Okay, so we will use the logic gates. So this half adder, you can make it by using this diodes, you can make this by using transistors, you can make this by using multiplexers also. But here what we are doing, we are implementing this half adder using the logic gates. Okay, so if we see the output of the sum, so we need two inputs A and B. So if we see the output of the sum, which gate it reminds you of?
And gate.
And gate.
Some part.
XOR gate.
Yes. So what was there in XOR gate we studied earlier? Just open XOR gate.
Ma'am, if both are in other state only, then it'll give a high output, ma'am.
Good. So in XOR gate, what we saw, if we have 0 0, then 0 0 or 1 1, it will give a 0. If both inputs are different, then only we will get a 1. Okay. So in XOR gate also we can, yesterday we saw, either we can make a circuit directly like this using an XOR gate, or we can make a circuit by using so many AND gates, OR gates, or NOT gates. But this will become like more number of ICs will be required, or more number of this logic gates will be required. So what we do, we simply make this, we use this XOR gate. So this is predefined. Okay, so for the sum, we will use an XOR gate. And what is this remind? What is the output if we see for carry? Which gate we will only get one when we have all the inputs as one?
And gate.
Okay, good. So this carry, we can say it as an AND gate. Okay. So we have to make this circuit. We have to perform this half adder. So we will use a XOR gate for sum, and we will use a AND gate for carry. Okay. We have to just get these outputs. So this is actually the theory. So we have to make this half adder using this logic gates. So if we see the output of the sum, we will see it is an XOR gate, output for XOR gate. And if we see the carry, we can see that it is a combination of AND gate. You can also use this sum of products, and you can make this gate. But by seeing the output, we can say this is an XOR gate. So if we use sum of products, we can say that only for sum, only this case is working, sorry, only this case is working, and only this case is working. Okay, so this will become our first case, and this will become our second case. So what will be the input combination for this? 0 1. So what will be the combination, input combination? It will be A dash into B. And the input combination for this second case, it will be A into B dash. Okay, or A into B bar. So these are the two cases. And then what we have to do, if we do sum of the products, so if we have to add these two cases. Okay, so we can say it is an XOR gate. We can make a gate using this AND gate. Here we have one AND gate, here we have one AND gate, and we have to use two NOT gates for this A dash and B dash, or A bar or B bar. Okay, and one OR gate for this plus sign. So why to use that much gates? Okay, so we can simply say it is an XOR gate. So we will make the circuit, and for carry, we can only say one min term in this last case. Okay. So what is the combination for this? It will be A into B. So what is A into B? That is an AND gate. So simply we will make this half adder using an XOR gate for sum, and for carry we will use an AND gate. Okay. Any doubt in this? How we are taking the gates? How we are
So
implementing? So this is a final circuit. Okay, we will take two inputs A and B. For sum, we will use an XOR gate, and for carry, we will use an AND gate. Okay, so we have to get this table. However you do use logic gates, you use transistors, use diodes, you do anything, or you use multiplexer. You can even do this with decoder, but you have to get these outputs only. Okay, so we will do this in logisim. So we are using this XOR gate. We can even use these many gates, okay? But what it will become very big circuit. So that's why we try to simplify the circuit. So we will use this circuit. We will simply use this XOR gate. So for 0, 0, 0, 0, the sum is 0 and the carry is also 0. We can see through the truth table. For 0, 1, our sum is 1 and the carry is 0. For 1, 0 also sum is 1 and the carry is 0. And for 1, 1, as we are getting this part, 1 plus 1, we are getting 1, 0. So our carry we are getting as 1. This carry we are getting as 1 and the sum we are getting it as 0. So if we do 0, 1, we can say sum we are getting as 1. So this is an IC. So inside this IC, this type of circuit will be put. Okay. So this big circuit will become very small, one IC. So here we are using two ICs, one for XOR and one for AND. So if we use a single IC, so the space will become very less. So for 1, 0 also, the sum is 1 and the carry is 0. And for 1 plus 1, the sum is becoming 0 and the carry is becoming 1. Okay. Any doubt in this half adder? Any doubt in this half adder?
No, ma'am.
No, ma'am.
Uh, So we will start with this full adder. In a half adder, what it was there, we were only adding two inputs, but in full adder we have to add three inputs. Okay, so here we are having three inputs and two outputs. One is sum and one is carry. Okay, so with half adder only, you can actually because we are getting one sum and carry. Okay, so with half adder only you can, if we combine two three half adders you can make a, sorry, if we add two three full adders you can make, like for one bit number. So this A and B, these are one bit now, only one bit is there. So with this full adder only you can uh, add this 3-bit numbers. But so what we will do to add 2-bit numbers, what we will do, we will cascade this full adder. We will put one after the other in series and we can add 2-bit numbers. For 3-bit numbers we will add three of this adders. Okay, and we can add 3-bit numbers. For 4-bit number, if we have to add 4-bit numbers, we will put this full adder 4-bit adders. So that's why we are not going beyond this full adder. Okay, we are only using two inputs, because with this full adder you can add 2-bit, 3-bit, 4-bit, 8-bit numbers using this full adder. That's why we are not going beyond this three input this beyond this three input adders. Okay, so first two inputs are A, B. So some places we write carry as C. So that's why we are using here carry as CI. Sorry, I'm not written here. It will be CI and output will be C0. CO, sorry. So we have to add this 3-bit numbers. Okay. So if we are adding this three inputs, so a plus b plus ci. Okay. So if we add 0 plus 0 plus 0, what will be the sum? What will be the sum for 0 plus 0 plus 0?
0,
And carry?
0,
0,
If we add 0 plus 0 plus 1, so what will be the sum?
1,
1,
And carry?
0,
So if we add 0 plus 1 plus 0, then what will be the sum?
1,
And carry?
0,
And here we have two ones. Okay. If we add 0 plus 1, so what will be the sum?
0,
Because here we are adding this part. Okay, 1 plus 1. So sum we are getting as 0 and the carry we are getting as 1. Okay, so here sum will be 0 and carry will be 1. If we add 1 plus 0, then what will be the sum?
1,
Carry.
0,
If we add 1 plus 0 plus 1, then sum.
sum 0 and carry 1,
And if we add this last term, 1 plus 1 plus 1, what will be the sum?
sum 1 and carry 1,
Hmm. So because here, if we add three numbers, 1 plus 1, so it becomes a 3. Okay. So here it will be 2 to the power 0 and here it will be 2 to the power 1. So 2 plus 1, it will be 3. So if we convert this binary into this decimal, so this is 3. And I will show you in the representation also how we are representing 3 as 1 1. That's why we are taking 3 as 1 1. Okay. So for sum, to make a circuit out of sum, what we will do, we will consider all the cases where we are getting a 1. Okay. So we will do sum of product. So this is our first case, this is our second case, this is our third case, and this is our fourth case. And for carry, we will only consider those where we are getting a 1. Okay, for making the carry circuit, what we will do, we will consider this case, we will consider this case, we will consider this case, and we will consider this case. So total number of cases are 4 for each: 1, 2, 3, 4, and 1, 2, 3, 4. So for making a circuit of sum, here we are getting a 1, so it will be a dash into b dash into c. For here we are getting a 1, so it will be a dash into b into c dash, or a bar b into b into c bar. Here will be a into b bar into c bar, and this last will be abc. Okay. So we will take all these min terms. So we will combine all these min terms with all these products with a sum. So we will add all these terms using sum of products. So what we will say, if we simplify this, we will get an XOR gate. Okay. Simplification is not in the syllabus, so that's why we are only using this XOR gate. Just remember this. For this is a uh, like a full. If you don't simplify and if you take the XOR gate for 3-bit input, this is what we will get. Okay. And for carry, these are the four cases we are getting. So here we are getting a 1, so it will be a bar into b into c. This will be a a into b bar into c. This will be a into b into c bar, and this is also the last case, so it will be uh, a into b into c. Okay. So if you use this carry, if you see this carry part, you can we can simplify this into ab into bc into ca. Okay. I will just show you how we are simplifying it. I thought of putting this, but it is not. If we simplify it, it becomes very lengthy. That's why I'm telling you, just remember this part. Okay, see, if we simplify the sum, they have used the simplification using this K map, but we are not studying this K map. Okay, we don't have this in syllabus. So if we go on simplifying this, it will become A XOR B XOR C. So this is our first part. Okay, and if we simplify using K map, so it will become AB into BC into CA. Some simplification will be there. See, uh, for this carry, if we simplify like this, like we have to put B into B dash and A into A dash, because that is also 1. So if we simplify it, it will become like this: AB into BC into CA. Here they have taken one common and taken this out. So we will get this part. Okay. So that's why I'm not telling you simplification. It is not in the syllabus. So if we simplify this part, it will become AB into BC into CA. One more thing they have done, what they have done in the book, I will just tell you. There is a question in the book. So there is a question. A logic circuit is to be constructed that will produce a logic 1 output whenever two or more of the three inputs are at logic 1. Okay. So this is a table for the carry. If uh, so this is the table for the carry. Okay, if two or more inputs are there, two or more ones are there, so we will get a 1. Okay, so that is a carry table. So here we can see we have 0 0 0, so no two ones are there, so we will get a 0. Only one is there, that's why we are getting a 0. Only one is there, so we are getting a 0. But if two are there, two ones are there, then we are getting a 1. Okay, so here also only one is there, so we are getting a 0. Here we are having two ones, so we are getting a 1. Here we are having two ones, so we are getting a 1. And here also we are having two ones, so we are getting a 1. Okay. So what they have done in sum of products, they have eliminated the zero part. Wherever we have, because the combination will be a dash into uh, a dash into b into c, it will be a dash into b into c. So what they have done, they have eliminated this part. So this is also one part of simplification. Okay, they have only considered this one terms. So first term will become bc, the second term will become ac, they have eliminated this b bar. This third term, it will become a into b, and this last term is will become abc. Okay, so as abc all are universal, so we can remove this term. Okay, abc. So what will be the I using sum of products? It will be bc into ac into ab into a plus b plus c. So to make a circuit, we can eliminate this abc part. Okay, so this is the first AND gate. This is for AC. So we have taken a and we have taken a C. So this is the first AND gate. So second part is AB. So we have taken this second AND gate for AB. So we have taken this. We have taken A and we have taken a B. So our output is coming as AB, and this third circuit we are getting a BC. Okay, so we have taken a B from here, we have taken a C directly from here. So we are getting a BC. Then what it is there? It is BC plus AC plus AB. So plus plus is there, means we have a OR gate. So we will put a 3-input OR gate and we will connect all these terms. So total we are getting as AC plus AB plus BC. So this is a carry circuit. Any doubt in this? Any doubt how we are getting a carry circuit? This can come in exam. Like we have used sum of products. Okay, what they have said, we will get logic 1 wherever 2 or 3 inputs are logic 1. So that is a carry. This is a carry part. So wherever 2 is there, so 1 plus 1, we will be getting a 1 0. So we are not using a sum, we are only using a carry. So this is one type of output we can get through the combinations of input. So here we have 2, that's why we are getting a 1. Here we have two ones, that's why we are getting a 1. Here we have two ones, that's why we are getting a 1. And here we have three ones, that's why we are getting a 1. Because 2 or more of 3 inputs we have said. Okay. So what they have, we will use sum of products whenever there is a one. We will consider all those cases. So here we have this. It is a dash into b into c. But what they have done, they have eliminated this dash part. Wherever there are zero, they have eliminated it. So it will become bc. Here it will become AC, here it will become AB, and here it will become ABC. So the output will be sum of products. So products we have, we will sum all the products. As ABC is universal, we can say it is a 1, so we will not use this ABC. So this is the full circuit for our carry part. Okay. Any doubt in this? So this is how we are making this carry circuit. And for the sum, we are getting from this min terms, from the sum of products, we are getting this. So that is an XOR gate. So we will simply make it as into XOR gate. Okay. So if we have to make a circuit from this logic gates, so we will do A XOR B, and the output of this we will do A XOR B XOR C. So this is how we will get a sum, and I explained you how we will get a carry. We will AND get this. So here we will get AC into here. I think you are getting BC into AB into AC. Okay. So we will OR gate all this, and we will get a carry. So this is the theory. These are the three inputs we have to get a sum and carry, and we are using this logic gates to make a full adder. Okay. So we will do this in Logisim. So if we give here, we will see the table. So here we will see the table for 0, 0, 0, we are getting sum of 0. For 1, we are getting a sum of 1. And wherever two inputs are there, we will get a 0 and the sum, and a carry as 1. Okay. So we do 0, 0, 0, sum is 0 and carry is also 0. 0, 0, 1, sum is 1 and carry is 0. If only one is there, so we will get a sum as 1. But if two ones are there, we will get a carry 1 and a sum 0, because it is becoming 1 0. So here we will use 2, then we are getting a carry of 1 and sum of 0. Or if we use AC, then we are getting a sum of 0 and of a carry of 1. But if we do 1 plus 1 plus 1, then the sum will be 1 and the carry will also be 1. Through IC I will show, we will get a sum of 1 and we will also get a carry of 1. Okay. So this is how we are implementing this full adder using logic gates. So this is our table, and to make our sum and carry, we will use the sum of products. Wherever we are getting a 1, we will use that circuit, and we will make this full adder. Any doubt how we got the circuit? So we will implement this full adder using this half adder. This is in your book. So this is the circuit. If you implement two half adders, so we will put this first half adder, and if we will put this second half adder, and we will get a sum and carry. So same thing you will get. So this is implementation of full adders using this half adder. It will, if we make the circuit, it will, I think it will work, but I have not made the circuit, so it will take time. Okay. So here also you will get the same outputs as you are getting here. So this is implementation of full adders using two half adders. So this is the circuit from the book. Just remember the circuit. You have to put A, B, C in first half adder, and the sum part we will put it as the input of second half adder, and this C input will go in the input of this second half adder, and directly we will get a sum, and both the carries we have to OR gate. So we will get a carry. So it will also give same output. Okay, this is from the book, so just remember the circuit. If we are, you will get a full adder using two half adders, you have to draw this circuit. So this we have done. This is for carry. This was in your book, so it can come in exam. Just go through the assignment. If this question is there, so it will come in the exam. Okay. So I have finished for today's class. You can write your roll numbers and leave. Any doubt? And please go through your assignments and start doing the assignments. It should be submitted by Monday.
Ma'am, are you posting the assignments in the GCR, ma'am?
I will post it today, by today.
Okay, ma'am.
Questions are there. I think in questions it is there.
Okay, ma'am.
So for one question, whatever you can do it in one page so that you can take a picture and you can upload it. And do this logisim. Try to do all the circuits. It will be easier for you to understand. Okay. Logisim, or if you don't have laptop, then do it in this mobile logic simulator.